Good morning to everyone. Today we are discussing about the types of optical fibers and attenuation in optical fibers and applications of optical fibers. So in last class, we will discuss about the uh, construction and principle of optical fiber and numerical aperture of the optical fiber, acceptance angle and relation between the numerical aperture and fractional refractive index change. Now, what is optical fiber? Optical fiber is a transparent guiding medium or system. Okay. Uh, Optical fiber is a cylindrical waveguide system which is operated at optical frequencies. It consists of mainly three parts: core, cladding, and protective jacket. And now the working or principle of optical fiber. Okay, principle of optical fiber is total internal reflection, which is possible when instant angle is greater than the critical angle. Now, what are the conditions for the total internal reflection? That is, first, the light ray travel from the denser to rarer medium, and the refractive index is N1 is greater than N2 means always the light ray travel from denser to rarer medium means high refractive index medium to low refractive index medium, and the angle of incident is greater than the critical angle. These are the conditions for the total internal reflection. After that, we derive the equation for the acceptance angle. Now, what is acceptance angle? Acceptance angle. Acceptance angle is the maximum angle of incidence at air core interface for which the light ray enter into the core and traverses along the core cladding interface is called the acceptance angle. Uh, Equation for the acceptance angle, that is IM is equal to sine inverse of under root of n1 square minus n2 square by n naught. Here n1 is the refractive index of the core and n2 is the refractive index of the cladding and n naught is the refractive index of the air medium. And this is the acceptance cone and numerical aperture. Numerical aperture means the light gathering capacity of the fiber is called numerical aperture. It measures the amount of light that can be accepted by the fiber. Okay. And numerical aperture is equal to the sine of the acceptance angle. That is sine IM. IM is the angle of acceptance angle. So from this NA, numerical aperture is equal to under root of N1 square minus N2 square by N. This is the expression for the numerical aperture. Okay. Next, relation between the numerical aperture and fractional refractive index change. Fractional refractive index change delta is equal to N1 minus N2 by N1 and a numerical aperture NA is equal to under root of N1 square minus N2 square by N naught. N naught is a refractive index of the air that is equal to 1. So the relation between the NA and delta is equal to NA is equal to N1 into under root of 2 delta. Okay, this is the relation between the numerical aperture and fractional index change. So now today's topic is types of optical fibers. So here the optical fibers classified into three major categories based on the material and based on the number of modes of propagation and based on the refractive index profile. Okay. First, based on the material, the optical fibers are classified into two types, that is glass fiber and plastic fiber. And based on the number of modes of propagation, okay, modes of propagation, they are divided into two types, single mode of fiber and multi-mode fiber. Okay, single mode optical fiber and multi-mode optical fiber. And third category వచ్చేసి based on the refractive index profile. Okay, refractive index profile. Uh, the, these are divided into two types, step index fiber and grade index fiber. Okay, so single mode fiber based on the number of modes of propagation, they are divided into two types, single mode and multi-mode. Now, what is single mode fiber? In a fiber, if only one mode of propagation is possible, Okay, in fiber, if only one mode is transmitted through the optical fiber, then it is called single mode of fiber. Okay, optical fiber lo single mode of propagation is possible అవుతుందని single mode optical fiber అంటాం. Multimode means if more than one mode is transmitted through optical fiber, then it is called multimode of optical fiber. If single mode of propagation is possible, single mode optical fiber. If more than one mode of propagation is possible, that is called multimode of optical fiber. Now see the differences between the single mode and multimode optical fibers. Okay. In single mode optical fibers, there is only one path for ray propagation. So there is only one path for ray propagation. See here. Okay. Single mode fiber. Okay. In multimode optical fibers, large number of paths are available for light ray propagation. Okay. Large number of light rays are propagated. See in the diagram. Okay. This is the single mode propagation. This is the multimode propagation. Second one, in single mode step index fibers have core diameter is less than 10 micrometer, and the difference between the refractive indices of core and cladding is very small. Okay, in single mode optical fiber, the diameter of the core is very less. That's why only single mode of propagation is possible. And the difference between the refractive indices of core and cladding means N1 minus N2 is very small. When N1 minus N2 is small, automatically the numerical aperture is also very small. See here, in multimode step index fiber, the core have diameter 50 to 200 micrometers. So here the core having the large diameter, so multimode of propagation is possible. And the difference between the refractive indices of core and cladding is very large. So N1 minus N2 is large and automatically the numerical aperture is also very large. Signal transmission capacity is less, but the single mode optical fibers are suitable for long distance communications. Okay, in single mode optical fibers, the transmission of signal capacity is less, but the single mode optical fibers are suitable for the long distance communications. Whereas in multimode, the signal transmission capacity is more in multimode fibers because of large dispersion and attenuation. They are less suitable for the long distance communications. For shorter distance communications, we use single mode optical fibers. For longer distance communication, we use single mode optical fibers. For longer distance communication, we do not use the multimode optical fibers. These are less suitable for the long distance communications. And these fifth one, launching of light into the single mode optical fiber is difficult. So launching of light means when the light ray enter into the core is very difficult because the diameter of the core is very less. Here the launching of light into the multimode optical fiber is easy because the core diameter is large. Sixth one, fabrication cost is very high in single mode optical fibers, and the fabrication cost is very less in multimode optical fibers. Okay, now see the diagrams. Okay, this is a single mode optical fiber. The core, this is the core and this is the cladding. The core diameter is 8 to 10 micrometer. And this is a cladding 125 micrometer. Whereas in multimode optical fiber, see here, the core diameter is 50 micrometer and here 62.5 micrometer. Okay, total the core diameter is 125 micrometer. Sorry, cladding diameter is 125 micrometer. Core is 50 micrometer, cladding is 125 micrometer. So because of this less core diameter, single ray of propagation is possible. See here, single mode of propagation is possible in single mode optical fibers. Because of large core diameter, multi-mode of propagation is possible in multi-mode optical fibers. Now see the third category based on the refractive index. The optical fibers are divided into two types, step index and gradient index optical fibers. Now see first about step index optical fiber. If the refractive index difference in the core and cladding is varied step by step, then the fiber is called step index optical fiber. See here in the diagram. In step index optical fibers, the refractive index of the core is throughout the core is same, that is unity. Okay, the refractive index is throughout the core same, and the refractive index is change decreases from core to cladding in the form of a step. See in the diagram in the form of a step. So that's why these are called step index optical fibers. Gradient index optical fiber. If the refractive index difference in the core and cladding is gradually varied in a number of small decreasing index steps, then the fiber is called gradient index fiber. In gradient index optical fiber, the refractive index is maximum at the center of the core. Okay, the refractive index is maximum at the center of the core and decreases towards the core cladding interface in a parabolic manner. Okay, here the refractive index is maximum at the center of the core. When moving from center to core cladding interface, that is decreases. The decreasing in a parabolic manner. See in the refractive index profile diagram. So here the refractive index is decreases like this. Okay, this is about the gradient index optical fiber. Now see intermodal dispersion. This intermodal dispersion is occurs only in multimode fibers. Now see what is intermodal dispersion. In each mode travels at different speeds inside the fibers. So they do not exit from the fiber at the same time. Therefore, the optical pulse is broadened in time as it travels along the multimode fiber. This pulse broadening effect is known as modal dispersion, is significantly observed in step index multimode fibers. This modal dispersion is occurs only observed in only single mode, step index multimode fibers. See, this is the step index multimode fibers. Okay, this signal intermodal dispersion. Next, step index single mode fiber. So again, the step index fibers are divided into two types, step index single mode fiber and step index multimode fibers. Okay. Okay, this is the step index single mode fiber and step index multimode fiber. Single mode step index fiber. The core diameter of this fiber is about 8 to 10 micrometer and outer diameter of cladding is 60 to 70 micrometer. There is only one path for ray propagation and hence it is known as single mode optical fiber. In this fiber, the transmission of light is by successive total internal reflection. It is reflective type. And these are extensively used in the world. Lasers are used as a light sources in these fibers. These are mainly used in the submarine cable systems. Okay, this is the single mode step index optical fiber. The core diameter is very small, that is 8 to 10 micrometer. And here because of this less core diameter, the single mode of propagation is possible. The ray propagation is almost axial propagation. And these are used in submarine cable systems. Now see what are the advantages of single mode step index optical fibers. It has very high capacity and the 80% of all fibers that are manufactured in the world today are of this type. And disadvantages, in spite of so many good qualities, the use of very thin cores creates mechanical difficulties in the manufacture and handling. Hence, this type of fiber is very expensive. Okay, this is the step index, refractive index profile diagram, and this is the radial distance, and this is the ray propagation, the light ray propagation, single mode step index optical fiber, the ray propagation. Next, step index multimode fiber. In this core, in these fibers, the core and cladding diameters are larger to have many paths for the light ray propagation. So the core and cladding diameters are large compared to the single mode step index fiber. So multimode of propagation is possible in these fibers. The core diameter varies from 50 to 200 micrometer and cladding diameter varies from 100 to 200 micrometer. The light ray propagates to the light ray propagates through multiple total internal reflections. These are used in data links for lower bandwidth measurements. You can now see the diagram. Refractive index profile for the step index multimode optical fiber. So here, see this, the core diameter is very large compared to the single mode, that is 50 to 60 micrometer, and the cladding is 25 to 300 micrometer. And this is a cross-sectional view of the multimode step index optical fiber. So multimodes are propagate, many light rays are propagate through this fiber. See here. Next, ray propagation. Now see the ray propagation in step index multimode fiber. The light ray is transmitted in digital form and the propagation of pulse is as shown in figure. Now see, the pulse which travels along the path 1 will reach first at the other end of the fiber. The pulse that travels along the path 1 zigzag reaches the other end with some time delay. Lastly, the pulse that travels along the path 3 reaches to the other end. See here. See here, this is the ray 1. We consider the ray 1. This is the ray 1. So the ray enter into the core. It makes the lesser angle with the fiber axis and enter into the core and instanted core cladding interface and it undergoes total internal reflection. And this ray at the output first we receive the first ray and means this ray. Okay. Now see second ray. So the first ray makes the less reflections in the fiber. See second ray. The second ray makes the greater angle with fiber axis and makes the more reflections in the fiber. Okay, see here 1 and 2. It makes the more reflections in the fiber. At the output we receive later we receive the second ray. So lastly the pulse that travels along the path 3 reaches the other end. So hence the pulsed signal received at the other end is broad-ended. This is known as modal dispersion. So the time delay is there between the first ray and second ray. Because of this, the modal dispersion is created. Now see the advantages. Since LED is used as a source of light, they are easier to make and they are less expensive and require less complex circuitry. Third one, they have longer lifetime than the laser diodes, thus making them more desirable in many applications. Next, fourth one, it is the least expensive of all the fibers. These are the advantages. Now see the disadvantages. They suffer from intermodal dispersion loss or transmit time dispersion. Okay. Uses, they are widely used in data links which requires low bandwidth. This is about the step index multimode optical fibers. Now see the grade index optical fiber. In this fiber, the refractive index decreases continuously from the center to the interface of core cladding. So at the center of the core, the refractive index is high. When we moving from center to core cladding interface, that is decreasing. The diameter of the core varies from 50 to 200 micrometer, and that of the cladding varies from 100 to 250 micrometer. The propagation of light ray in grain index follows a parabolic path. See here, parabolic path. So at the center of the core, the refractive index is high. So when moving core cladding interface towards core cladding interface, that is decreases like this in a parabolic manner. The grade index fiber, the light ray travels at different speeds in different parts of the fiber. So in the grade index fiber, the refractive index is changed, not constant throughout the core. So with different, the light ray travels different speeds at different parts of the fiber. Near the outer surface, uh, the RI is small. That means the refractive index is small near the outer surface. Hence, the rays travel at greater speed than the rays travel at the core. Thus, all the rays arrive at the receiving end of the optical fiber at the same time. See here, in grain-dex optical fiber, only multimode of propagation is possible. So, when light ray enter into the core, see this ray, the ray travel near the fiber axis. And it means that means uh, center of the core. Okay, near the fiber axis, the refractive index is high. At the center of the core, the refractive index is high. When the ray travel near the fiber axis with lesser speed, because here the refractive index is high. Where the ray travel uh, near the outer surface, the ray travel with high speed because here the refractive index is low. Okay, here see this, the ray here, the first ray travel in the lesser path. Okay, travel in the lesser path, short path. Here the ray travel in the longer path. But at the output, both rays are received at the same time. Why? Because here the refractive index is high. That's why the light velocity is decreased. The ray 2 makes travel in the longer distance. But here the refractive index is low. Because of this, the light velocity is more. So at the output, we receive the both rays are same time at the same time. So thus all the rays arrive at the receiving end of the optical fiber at the same time. These fibers are used in telephone trunks between the telephone exchanges in different cities. For example, fiber to home connections from BSNL, Reliance, Geo, etc. These are the live examples. And now see the advantages of grade index optical fibers. Intermodal dispersion can be reduced by using this type of fiber. So already we see this intermodal dispersion. Okay, this intermodal dispersion is very less in this grade index optical fiber, and it is high quality fiber. Now see the disadvantages. It is the most expensive of all type of fibers, and its splicing could be done with some difficulty. Splicing means joining. So joining could be done with some difficulty. Applications and uses. So main applications are communication and medical and industry. Optical fibers find their applications in the field of communication and medicine and industry. Now, see the differences between the step index optical fiber and grade index optical fiber. Okay. See first point. The refractive index of core is uniform, and step or abrupt change refractive index takes place at the interface of core cladding in step index optical fiber. Okay. The refractive index of the core is uniform. Core refractive index అనేది throughout the course same ఉంటుంది, and it is decreases in the form of a step. So that's why these are called step index optical fibers. Whereas in grade index optical fiber, refractive index of core is non-uniform. It is maximum at the center of the core and moving towards outer surface, it is decreases in a parabolic manner. So uh, from the axis of the core to its surface. See, the refractive index of the core is non-uniform and it is decreases parabolically from the axis of the core to its surface. Second point, the light ray propagates in zigzag manner inside the core. The rays travel in the fiber or meridional rays and they cross the fiber axis for every reflections. Okay, in step index optical fiber, the ray propagation is zigzag manner. See here. Okay, like this zigzag manner. And the ray travels in the fiber or meridional rays. Meridional rays means which rays are cross the axis and travel. These rays are called meridional rays. Okay. The rays travel in the fiber or meridional rays and they cross the fiber axis for every reflection. Whereas in gray index optical fiber, the light ray propagate in the form of skew rays or helical rays. They will not cross the fiber. Okay. Helical rays. In gray index optical fiber, the ray propagation is helical. See here, see in the diagram like this. So these are not cross the fiber axis. So third one, signal distortion is more in case of high angle rays in multimode step index fiber. Okay, signal distortion is more in case of high angle ray in multimode step index fiber. In single mode step index fiber, there is no distortion. Signal distortion is very low. Even the rays travel with different speeds inside the fiber. The bandwidth is about 50 megahertz per kilometer for multimode in multimode step index fiber, where it is more than 1000 megahertz in case of single mode optical fibers. Sorry, single mode step index optical fibers. So single mode step multimode optical fibers, the bandwidth is 50 megahertz. In single mode step index optical fiber, the bandwidth is 1000 megahertz, more than 1000 megahertz. The bandwidth of fiber lies in between the 200 to 600 megahertz per kilometer, even though theoretically it has an infinite bandwidth. So gray index optical fibers having high bandwidth. Attenuation is more in multimode step index optical fiber and it is less in single mode optical fiber. So attenuation means loss. Okay, attenuation is more in the multimode step index optical fiber and it is less in the single mode step index optical fiber. Now gray index optical fiber, attenuation of light rays is very less in gray index optical fiber. And numerical aperture of multimode step index fiber is more, whereas in single mode optical fiber, because in multimode step index optical fiber, N1 minus N2 is large. Sorry, N1 minus N2 is large. Whereas in single mode step index optical fiber, the N1 minus N2 is small. So numerical aperture is also small. Gradient index optical fiber, numerical aperture of gradient index optical fibers is very less. NA is very less. This is about the differences between the step index optical fiber and gradient index optical fiber. Now see the attenuations in optical fibers. It is the ratio of input optical power into the fiber to the power of light coming out at the output end. Okay, it is the ratio of input optical power, that is Pi, into the fiber to the power of light coming out at the output end. Okay, attenuation coefficient is given as alpha, that is equal 10 by L log base 10 Pi by P naught. Pi means input optical power into the fiber and P naught is the power of light at the output end. and decibels per kilometer. Okay, here L is the length of the cable. This is about the attenuation in optical fibers. Now see, the attenuation is mainly due to three reasons: absorption, scattering, and bending. Okay, absorption losses in glass fibers, three different absorption takes place. First one, ultraviolet absorption. Absorption of UV radiation around 0.14 micrometer results in the ionization of valence electrons. Okay, this is the UV absorption. Second one, infrared absorption. Absorption of IR photons by atoms within the within the glass molecules causes heating. This produces the absorption peak at 8 micrometer, also minor peaks at 3.2, 3.8, and 4.4 micrometer. So infrared absorption this is about the infrared absorption. And ion resonance or OH absorption. The OH ions of water trapped during manufacturing causes absorption at 0.95, 1.25, and 3.9, 1.39 micrometer. Next, scattering losses. The molten glass, when it is converted into thin fiber under proper tension, creates the submicroscopic variations in the density of glass, leads to the losses. Okay. Uh, Second one, the dopant added to the glass to vary the refractive index also leads to the inhomogeneity inhomogeneities in the fiber. As a result, loss occurs. Scattering losses are inversely proportional to the fourth power of the lambda. Okay, this is the graph shown for the wavelength versus attenuation. Okay. Okay, this is the absorption, impurity absorption, and scattering absorption, heterogeneous structure scattering, and this is the bending losses. Okay, now third one, bending losses. In a bent fiber, there is a loss in power of the transmitted signal called as bending losses. According to the theory of light, the part of the wavefront traveling in the cladding means rarer medium, should travel with more velocity than wavefront in the core. Core means here denser medium. But according to Einstein theory of relativity, in a single wavefront, one part should not travel with higher velocity than the other part. So the part of wavefront traveling in cladding medium lost in the form of radiation leads to the bending losses. Now see here the macro bending and this is the micro bending. So when fiber is bent, the light does not participate in the total internal reflection and escape from the fiber. Okay, this is the escaping ray. Same here also, this is a microscopic bend. Here also the light does not participate in the total and internal reflection and escape from the fiber. Okay, this is about the attenuation, uh, causes for attenuation, absorption, scattering, and bending. Now see applications of optical fibers in different fields. Optical fibers are extensively used in communication system. Optical fibers are in exchange of information between different computers, and these are used for exchange of information in cables, cable televisions, space vehicles, submarines, and these are used in industry in security alarm system, process control, and industrial automations. And also these are used in pressure sensors in biomedical and engine control. And optical fibers are used in medicine, in the fabrication, in endoscopy for the visualization of internal parts of the human body. And sensing applications of optical fibers are displacement sensors, fluid level detector, liquid level sensor, temperature and pressure sensors, and chemical sensors. And see the medical applications of optical fibers. These are used in gastroscope, arthroscope, etc. Okay, this is about the applications of optical fibers in different fields. So, thank you.